Hey, welcome back. So this week the world has been going absolutely crazy about the new DeepSeek R1 model. Now, if you haven't heard of it before, it is a open weight reasoning model from a company called DeepSeek in China. Now, the reason everybody is going crazy about it is they open weighted the model. It is available on Ollama. It's available in Hugging Face. You can run it on your machine. And they released a paper explaining how they actually trained the model, and it's an absolutely fascinating read. And it is fair to say the results from that model are incredible. In fact, if you check out one of my videos from last month, you can actually see a full breakdown from me on that video. But we're not going to focus on that today. We're actually going to focus on the part of the paper where they bootstrap the model with long chain of thoughts to elicit reasoning from the model. And it is such a cool part of the paper. In fact, what we are going to do is we're going to replicate a little bit of that part of the paper, and I'm going to show you how you're able to do that yourself. If you want to get started with it quickly and then just experiment a little bit, you can go to just chat.deepseek.com. It's got a sort of chat interface that you can interact with. So if you then just click on the DeepSeek R1 button there, then that will invoke the reasoning part. And I can just type in something like solve 91 minus 52 plus 90. And again, this is a kind of very simple math arithmetic thing. And again, I covered this in my other video, but the key thing about this is it invokes this sort of reasoning. Now, it's a fairly unstructured set of reasoning, and they actually talk about that in the paper, which we'll go through in a little bit. But you see there, it says, first I need to solve this expression, 91 minus 2 plus 90, blah, 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 blah. A little bit crazy, and then it will come back with the final answer. And again, I can kick off a new chat, and I can do something a little bit more complicated. So we'll say 2187 plus negative 9639, and then we're going to multiply that by negative 9466. A little bit more complicated, but again, it should be able to pick this up. And you see it's generating its chain of thought reasons there. Key thing is there, it's quite long. Okay, let's track with this problem. I first need to remember the operations, and then it's just going to sit and think about it and generate these tokens. And that's the sort of test time compute or inference time compute that OpenAI talks about. And you see it is generating a lot of tokens underneath the hood. It's working through alternatives, and then in the paper it can even sort of reflect when it gets wrong. Eventually, after a while, it's going to come back with an answer, and you see there it's figured out the answer is 7054632, and then it gives the final answer in some pretty markdown. Again, if I go into ChatGPT for a second, and then we paste the exact same question into ChatGPT, and then you can see, unlike the DeepSeek R1 models, ChatGPT hides the reasoning, the think tokens that you get there. I can click on this, and then it gives you a little bit of details, a summarized version, breaking down the steps, breaking down the calculations, combining the results. But as you can see, both come back with the same answer. Now, of course, if I want to, I can always download the models locally onto my machine via something like Ollama. So if I go to ollama.com library, click on DeepSeek R1, you can see they've got the smaller versions of the model, 1.5 billion parameter model, all the way up to the 671 billion parameter model. It defaults on the DeepSeek R1 7B model. And again, you can just pick whichever one you want to be able to work with. But once I have Ollama on my machine, I can just do Ollama run DeepSeek -R1. And then if I want to, I can ask the same question. So we'll maybe do the 2187 blah, blah, blah question there. And then again, it's going to go through that sort of same generation of tokens. But the nice thing about Ollama is I can read it a little bit more here. It says think, I need to calculate blah, 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 blah. And then everything within the think tags is actually those reasoning steps. Now you see it's doing a lot less reasoning than the models up on deepseek.com, probably because they're running the bigger models there, and therefore it's going to generate more reasoning tokens. As you say, eventually it comes back with the question, and then it says the answer is 7042272. As you may have gathered in this particular case, it's actually came back with the wrong answer, and mainly it's going to come back with the wrong answer because it's a smaller model, and actually it's just generated less tokens. If I want to, I can give it a slightly simpler calculation, which is to solve 91 minus 52 plus 91 that we did earlier, and you can see it's generating the tokens, and this time it will come back with the right answer, 129. So again, you're going to get different results based on the size of the model that you use, etc., etc. But you see it's pretty good. You can run it locally. Okay, so now that we've got a quick view of how kind of basic math actually works with DeepSeek, let's actually take a quick look at the paper and see what they've done. So you can download that. It's on archive, but you can also just download it from their GitHub, which is what we're going to do. And as you see, it's a really fascinating paper. You can just go through that and read it. The key thing that I want to sort of point out here is in section 2, where they talk about the approach that they did on the model. So the first thing is that they did reinforcement learning on the base model. So what they did is they took a pure base model, so not a chat model, not an instruct model. They took a base model without any sort of supervised data, so no supervised fine tuning, which is really incredible. And then they trained it just from rewards on the model from scratch. So they took the base model and then did reinforcement learning over the top of that, and the model learned for itself how to generate these long chain of thoughts. And that's pretty cool in itself. And again, they give their reinforcement learning algorithm, and again, you can kind of go through that. I will probably do a video at some point in the future where we will train reinforcement learning for ourselves and replicate what's actually going on here. And what's actually cool during that reinforcement learning process, and they give a bit of a view of how they've done it, is in the paper, they have a nice little prompt template that they use whilst training the model to invoke chain of thoughts. And it's actually pretty simple, which is a conversation between a user and an assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process and then provides the user with the answer. The reasoning process and answer enclosed within think tags and answer tags respectively, i.e. think, reason, process here, answer here. And then they put user, and this red prompt, that's where you would put the specific question that they want to ask during reinforcement learning, and then the assistant is going to churn it out. Now remember, they don't have a base model at this point, so the model hasn't been tuned to understand chat templates. So what they are doing here is they've sort of created a mini template to invoke user assistant prompts that you would sort of expect. And then they're just guiding the model to generate these think tags and these answer tags. Answer is what the user sees. Think is what is used for the reasoning process. And again, they've not fine-tuned that with any data. They're just guiding the model to produce the right results. And then they're using reinforcement learning to come back with those results. So it's never seen any long chain of thought prompts before. So I think that's super cool in itself, because then what they do is once you generate those chain of thoughts from the model, whether they're right or not is a different question, but they use sort of reward modeling to actually determine whether it was a good chain of thought. And the way they do this is through accuracy rewards and format rewards. So for accuracy, it evaluates whether the response is correct. For example, in the case of math problems with deterministic results, the model is required to provide the answer in a specified format, e.g. within a box, enabling reliable rule verification of correctness. So you can sort of imagine if you were saying, like in the example we had, if you do 25 plus 2, they are going to run that through a piece of code, run the calculation, and it's going to come back and say 7. So they will have in their little answer format, it will just say what the answer is, so like 27, and then they'll run that through their own verifier, and then they'll check that the answer is correct. If the answer is correct, they'll give it a reward. And again, as you can see here from the paper, it's saying similarly for leak code problems, a compiler can be used to generate feedback based on the predefined test cases. So essentially, they're going to do a compile, you get a reward if it compiles, and then they'll run the leak code test cases. If it comes back with a successful answer from the test, it's going to get a reward as well. And then the last thing is they're rewarding for is format rewards. In addition to accuracy reward model, we employ a format reward model that enforces the model to put its thinking process between think and think tags. Now, what we're going to do, we're not going to do reward modeling. We're going to do sort of generation of chain of thoughts, but I'm actually going to show you how this works in this video. So actually, we are going to train a base model to generate those think tags and to elicit reasoning. And we're also going to train a model to be able to do verification. So that whole answer thing that I showed you, I'm going to show you exactly how to do the same thing within this video. So that's pretty cool. They did that from scratch, really great. We'll do reinforcement learning on another video. But actually, the thing that I really want to talk about, and this is what we are going to do in this video, is they then did this thing called Coldstart. So they said here, inspired by the promising results DeepSeek R1 two natural questions arise. Can reasoning performance be further improved or convergence accelerated by incorporating a small amount of high quality data as a cold start? So what they're saying there is, rather than letting the model figure this out during reinforcement learning, they want to speed up the reinforcement learning process by saying, I'm going to get a small amount of supervised fine-tuning data, i.e. I'm going to get a set of prompts that give me roughly the answer that I need, and then I'm going to use that to sort of cold start the model, and then I'm going to take over reinforcement learning from there. And they're also saying that it gives a second benefit, that if they can sort of cold start with those chain of thoughts that they've pre-trained before, then it should give more clear and coherent chains of thought than previously. Remember when I did the DeepSeek R1 video last month, one of the things that we said is that the chain of thoughts were quite crazy. Well, actually, they're sort of saying they want to get even better, chain of thoughts generated, and they're using this cold start technique to be able to do that. And we're going to replicate this cold start technique in this video in about 2 minutes. So as you can see there, unlike DeepSeek R1 to prevent the early unstable cold start phase. So what they're saying there is that when they did reinforcement learning from scratch and having the model use that template to generate the long chain of thoughts, they were getting unstable answers, and it took them a long time to eventually get chain of thoughts in a format that they needed. And they think by using this small amount of fine-tuned data, they can therefore elicit better results from the beginning and come back with better results quicker. And again, as I said, I've reproduced this, and I'm going to show you this in about 2 minutes and how you can do it for yourself. And then they say here, in this work, we collect thousands of cold start data to fine tune. Remember what I said there, right? Most of these models are trillions of tokens to be able to train the base model. And even in fine tuning phase, it's usually millions and millions of tokens. They're saying for this cold start phase, thousands. And then finally, what they're saying there is once they've done the cold start phase as a sort of supervised fine tune, then they're going to just jump back into reinforcement learning, and it should be able to pick it up quicker from there. Okay, so the first thing that we need to be able to do is generate long chains of thought. Now, they didn't specify in the paper how they generated these long chain of thoughts that are accurate, but we can probably simulate this ourselves, right? Because the problem with things like math is that the steps, the chains of thought, need to be accurate. Now, if the model's not any good at doing math in the first place, so maybe something like the kind of O1 models, or maybe you've got a 400 billion parameter model or something like that, it's going to be not bad at math. But to be honest, it can still get things wrong. And yes, you're going to use a verifier and then sort of, sample reject anything that's got the wrong answer. You're going to remove from your list. So you can generate chains of thought that way. Just generate the chains of thought, and then anything that's not right, remove it, and then have a list of prompts for your fine tuning that is only accurate. But I think we can do a better way of doing that. Because we can use compilers and we can use abstract syntax trees to be able to generate steps within maths, then we can actually generate an accurate set of chain of thoughts ourselves. So I did a video earlier last year, which was on a thing called a math compiler. And what it actually did is generate a synthetic chains of thought for math. So we are going to use this to be able to generate the long chain of thoughts that we need. So if you can go onto my GitHub, and you can, it's the folder's called Chuck Math. I'll put it in the links. You can just download and run it. But you can kind of see what I mean here. So if I type in something like Python main.py, I'm in my Chuck Math folder, and then I do 91 minus 52 plus 90. If we run that for a second, it's going to generate a whole sort of, it's going to generate things like some instructions, so some sample questions. You can see there it generates out the tokens of the abstract syntax tree, but the key thing is here is it generates out an explanation. Now, it hasn't done anything with the large language model. I have a whole video explaining this, but I just want you to basically see that it goes step 0, 91 minus 52 equals 39. Step 1 is 39 plus 90 equals 129. And that actually is the key thing. I can just generate out these steps as I need. Again, we can do something a little bit more complicated, so we can put parentheses in here. So we'll say 2187. We'll add that minus 9639. So that gives us a little bit of a unary. I'm going to close the parenthesis. Then I'm going to do a multiplication, and we're going to say minus 9 9466. We will just close that off and we'll run that for a second. And then you can see in the explanation, step 0, 9639 minus 0 is equal to 9639. Step 1 is 2187 plus 9639. And it gives us the answer there. Step 2 is equal there, da 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 da. And then eventually gives the real answer, which is 11944916. So the key thing that I've got here is I've got the calculated answer and then I've got the steps. And again, we can use this to generate the long chain of thought there because we've got the steps, but there's just no explanation behind it at this stage. So now all I really need to do is actually get a large language model in on the business as well. So if I just do minus LLM, and then I put something like 5.4, which is kind of Microsoft's new model, and that's available on Ollama as well. We'll do a couple of different models there here. So what we're actually going to ask the LLM to do is not to calculate what the actual sum is for itself. What we're asking it to do is say, take the steps that I've just given you, and what I want you to then do is augment that with an explanation. So the LLM, doesn't matter if it's good or bad at math, that doesn't really matter because we're going to provide it the answer and we're going to provide it the steps and we're going to ask it just to go and figure all of this out. So you can see here it's come back and it says the calculation involves 2 main steps. Addition, start with this, blah, 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 blah. And then you see for the result, it's basically saying think. And I'm going to show you why I've got the think in here in a second. So you see this think, problem, resolve this, and note the result. Reasoning, start with the expression. According to PEMDAS, do this, 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 and this. And then eventually it's going to come back with the right answer. So 705, 40632. So I've given it a nice complicated sum for it to do, but I've added in the LLM and then it's going to reason how it got to that result. And again, we know the result is correct because even before the LLM, you see in this part here, result 705040632 is the same answer that the LLM has got. And then what I've done here is I've put the verifier answer within its own verifier tag. So later on, if I want to go and parse that, I can do this. So I've got my reasoning steps. So within here, I'm telling it to do its reasoning within the think. And then I'm going to be able to provide the answer in the answer tag. So you see in the answer tag, the result of blah, blah, blah is 7054. And then the verifier answer where it's cleaned of all the kind of preamble has this final answer here. So it's pretty cool. And again, I can do this with not just the 5.4 model. So if you're worried about, there's a lot of models you're not allowed to use to train other models. But if I want to, I can pick a model with a clean license. So in this case, I could pick the kind of the Granite 3.1 dense model. And the reason I'm picking that is an Apache license. So therefore, I can just do whatever I want with the outputs of that model. But again, you can use anything. I used 5.4 earlier. You could use Llama 3.3. You could use the Qwen models. All of that is equally fine. You just put in a different LLM. And then that LLM is simply, because it's not responsible for doing the calculations, it is just responsible for doing the translation. Then it's going to come back with that answer. So again, here, this one was the Granite model. And you see the result, same result as before. And now the Granite model's got its steps. Think. What is this? Blah, blah, blah. Here's its reasoning. And then it's worked through all of the steps. And then it's giving me my answer, my verifier answer. If we want to, we can actually look at the prompt template that powers this. And you can see here, I've got a math step-by-step prompt template that we've got here. And again, it's very simple. For the problem question involving the expression blah, produce a set of steps there. And then there's a few things I've added it to do. Restate the problem queerly using the think tags, break down the solution into logically ordered blah, blah, blah. I tell it to use things like PEMDAS, conclude the reason with the final answer inside the answer tags. And then for that verifier answer, I'm saying include a verifier answer section containing only the result formatted for automated systems. All reasoning must be within the think tags. No reasoning should occur outside those tags. And then think, and then there's the problem, and then the reasoning, and then in the tags, final answer, and then a clean answer used for verification. And again, I've also added in a recheck the steps and answer if there is a discrepancy. Now this whole reflection thing is really fascinating. So one of the things until I got this improved template is actually I had an earlier template which would occasionally come back with the wrong results because the steps weren't as clear until I improved it. But because I had this, go recheck and reperform the reasoning, it was actually able to correct itself within the prompt. And again, even in the data that I generate, anywhere where it gets it wrong or there's a discrepancy in steps, it can actually reflect the answers back. And now I'll demonstrate this with the slightly older template. So I'm just going to change in the code here the template name from math step-by-step template to this slightly older one. And now we are going to rerun this code. I'm going to use a slightly different sum because I'm going to use a sum that I know that's going to invoke this issue. So in this case, I'm going to put 8895 plus 631 divided by minus 659 plus minus 952. So this is a little bit of a tricky one there. We're going to run this again against the Grant 3.1 dense. Now, as I said, this was a version of the template that was slightly wrong and then didn't invoke the behavior that they wanted for generating these prompts. But look at what it does in the middle of this. Now, as you can see here, it started with the think and it's doing its questions there. But this is the key part here, right? It says, this gives us approximately 98479575. And the reason it's got it wrong is it did a wrong minusing a little bit earlier. And then it's just said here, however, upon reviewing the steps, I noticed a discrepancy in the final calculation. Let's correct this by recalculating the last step accurately. Recalculated step 3, adding the results from step 1 and 2 correctly gives us approximately 794.0425, and then and then you can see the final verifier answer is 794.0425. So it has reflected the answer and then got it correct. Now, if I come back into the DeepSeek paper, the thing that they were talking about is during the reinforcement learning process, is this thing called aha moment. So you see a question if A is greater than 1 and the sum of the blah, 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 blah. And again, that's more complicated in my example, but we can use the same technique to generate longer chains of thought this way. And then you see, wait, there's an aha moment I can flag. Well, let's reevaluate this step by step to identify the correct sum. So this is why I include some of this in my chains of thought here so that I can then have these sort of aha moments or these reflection moments. And you see it sort of works perfectly in that sense. Now, if I just switch the template back to the old template, it will still reflect. It just happens to be for this particular question, it actually gets it right straight off. However, in the training data set that I generated, there are reflection moments, and I'll show you them in a second. And there we go. You can see there with my slightly better template that it didn't need to reflect the answer because it was able to get the answer straight off itself without doing anything. So now that I've got a really good way of generating synthetic chains of thoughts, one of the things that I can do is then just generate them out. So just to be super quick here, what we will do is I've got a script within the math compiler, which is called generate chat samples. I am just going to change this to maybe 3 samples there to make it a little bit quick. I've got different levels of difficulty, very easy, hard, medium, etc. I can say which LLM I want to use, and then I'm just going to output it into a folder chat samples, and we'll just change this rather than it saying very easy. I'm just going to say record, and then what's actually going to happen is it's going to automatically put it into a chat format that I can use for fine tuning. So it will generate 3 samples. I'll show you what that looks like, and then what I'm going to do is show you a larger data set that I pre-generated, and we're going to then use the larger data set to fine tune. Okay, as you can see, it's completed that. So if I just come into Visual Studio Code for a second and we go into outputs, there's chat samples record, and you see it's generated in the standard chat format. Messages, role, user, what's blah, blah, 76 plus 5 for the arithmetic problem, blah, 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 blah. So it's done exactly what I wanted. It generated some samples. It's created random expressions because it can randomly generate math questions. And then it's then done what we did before. It's ran it through the LLM with all the explanations and steps. It's generated those think tags with the problem, the reasoning, etc. And then it's got those synthetic long chain of thought. So again, and I know the answers are going to be correct, and I know they're going to be correct because the answer is coming from the math compiler, not from the LLM. The LLM is just responsible for doing those steps. Now, what is very cool about this is when I run the chat samples earlier, you can see I generated, in this case, I generated 20 easy ones. So again, just using the same process that we did there. I generated hard ones. We didn't use hard in the dataset because I thought they were a little bit too complicated. But again, if I just look at the chat samples medium, this is the first question, which was calculate minus blah, 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 blah. But if you look here, just around halfway through there, it discovers an error. And then it then says, okay, I need to recheck the steps or discrepancies. And it says, however, upon reviewing the calculation, it appears there's an error. And then it fixes that error and generates the steps. So I generated a whole load of samples, like 120 or whatever different samples there. And then I sort of put them all into this merged file. So I have 120 different math samples with long chain of thoughts. And that is what we are going to use to fine tune. So now that we've got 120 rows of math data in the standard kind of chat format, one of the things that I need to do now, because I'm working with the Qwen model and because the Qwen model as a base model doesn't understand chat at this point, I wanted to simplify things a little bit, and rather than leaving the MLX fine-tune to be able to do the completions, one of the things that I did is convert it into the final format for fine-tuning myself. So I have a little script here called convert JSON-L, and all it does is take that format, so messages, role, user, assistant, and then converts it into a line that the MLX fine-tuning is going to understand. So you see in this case it's text, and then it's got a little token IM start, and then user content, IM end, IM start, assistant, and then assistant content. So it's just converting from this format into this format here, which the Qwen model, which we're going to use as our base model, will actually understand. So then what I did is I just paste that converted version. So it's the same 120 that I showed you earlier. And I put it in this Coldstart folder called Math with Reflection. And you see it's just IM start, blah, blah, blah. So it's basically the output of our generated chat format. Yep. So that is 120 rows of data, which is all fine-tuned. And this is going to be my Coldstart data. And then I take this file here, which is, I call it new.jsonl. In my Apple MLX fine-tuning video that I released last week, I have what I call a mixed data set, which teaches the model how to answer other different types of questions. So I've removed the math type questions from there, but you see it's got stuff like write a short horror story in 2 minutes, tell me a joke about coffee, what is the capital city of Japan, and then it's going to have a bunch of answers. The reason that I have this file is just so that the model doesn't forget how to perform certain tasks. This is a bad JSON-L. And the reason it's pretty bad is that all the answers are fairly short. And because all the answers are fairly short, when I ask the model questions like, who is Ada Lovelace or whatever, rather than give me a long answer, it's going to give me a very short answer. So in the future, what you would want to do here is build up a good set of mixed data set like the same way DeepSeek did, so that when I eventually have a Coldstart data, I have good math completions, and I have good ones that do summarization, I have good ones that write short stories, write poems, etc. And then eventually, and all of them invoking long chain of thoughts, and then eventually, if I get enough of a diverse data set, then I'm going to be able to Coldstart. Today, we're just doing the math piece. I haven't done code or anything like that, but I think it's going to be good enough for what I want to show. So then I run a little script, which is sort of a merge script. And then what the merge script does is it takes merge completions and it takes the new JSON-L, and then it puts the two things together and sort of shuffles it, and now I have that sort of mixed data set with all the various questions you see there, who was Albert Einstein, etc. But it's mixed in with those math questions. Calculate this, and then it's got that long chain of thought, etc. within there, and I can scroll across and you can see wherever the long chain of thought is. This is my merged JSON-L, and that's what I'm going to use to fine tune. And again, all of this data is up in my GitHub, so you can go and utilize it for yourself. Okay, so now that that's done, we are now going to try and interact with the various models. So I am going to do a UV run minus MLX LM dot chat. And again, in my other video, so in the MLX fine-tuning, I go into this in great detail. But in this particular case, we're going to attempt to chat with the Qwen 2.5 1.5 billion parameter model. This is a tiny model, 1.5 billion parameters, right? And I'm going to only get max tokens of 500 back. So we're going to enter into chat mode. And then the first thing you're going to see here is that the model really doesn't understand anything. So if I say what's 8895 plus 631 divided by minus 659 plus minus 952, and again, you can just see it's nonsense. The model just doesn't know how to do anything. It's not been trained on chat format. It certainly can't do math. What we are now going to do is take that 370 lines of boot-started data, the cold start data, and then we're going to fine-tune it with it. So to run the fine-tune, I'm going to do a UV run mlx_lm.loro. Again, that comes part of the Apple MLX. The model is going to be that 1.5 billion parameter model that we said. I'm going to train it. So that's minus train. I'm going to use the dataset Coldstart. I'll just show you that one more time. The learning rate is 1e minus 5. That's a sort of standard learning rate that you use for fine-tuning. I'm going to run it through 300 iterations, and then I'm going to do a full fine-tune. Again, I break it down in my other video. And again, just so there's kind of no shenanigans there, if you look in the dataset Coldstart, here's that same trained dataset, 300. It's got around 380 in this case. Yeah, but that's the same data that I was showing you earlier. It's that mixed dataset. So nothing too interesting there. It also needs a test JSON-L. I've just put some random, questions and answers in there and a valid one. So it can do its training validations. So it's going to pick up these three files here. All you're going to do is copy and paste the stuff that I showed you a little bit earlier. And then we are going to train that model. Alrighty, so I'm going to kick off the train on there. So you see it started the training there. It's going to do 300 iterations there. Validation loss is 4.9 at the moment. You see in my machine, it's quite a small model, so it's training at around 600 tokens per second. You see that training loss is going down as it does each iteration. It's, at 600, 700 tokens per second, it's not going to take very long to complete the training in this model. And again, this is because it's a super small model there. You see here, peak memory usage is around sort of 16 to 26 gig. So if you're running this on your machine, it might be a little bit too small. Yeah, so if you're running this on your machine, it might be a little bit too large for you. You can always use a quantized model, or you can use an even smaller model, maybe the 500 million parameter model, and you'll be able to do the same thing. I want to use a full train. I don't want to be doing any LoRa training. I'm not purposely using quantization, etc., because I want this to be as close as possible to fine-tuning a full model. Alrighty, as you can see there, it's literally just finished training there. So you can see through the training runs, that training losses went down. It's got better and better as time has went by, and then eventually it came down to sort of 0.7. So if you remember, my file had close enough to around 400 rows of data in there. If I'm doing 4 rows of data as a batch size, which is the batch size is 4, and it's doing 300 iterations, then that's roughly about 1200. So that means I'm really processing around 3 runs of my data. So I'm processing my data 3 times, or 3 epochs. Again, ideally, I would do 1 epoch, 1 run of data. So I would generate enough data with a nice balance so that I can only do that run 1 time. But again, I'm being super lazy in this sense. So I have a trained model now. If I just clear my screen for a second, you see within this folder here, adapters. So if I go into adapters, you will see these are the adapters. This is the difference between the old model model and new model, and then they get combined together to form my new model. Again, I cover that in my other video, but now if I want to, we can chat with that model. And a way that I chat with that model is exactly as how I did before. So I do UV run -m chat, so it's no different there. I pass in my model, which in this case is the Qwen2.5-1.5 billion parameter model, which I'm using as my base model. Max tokens in this case is 500, and then I just need to add in this extra thing, which is --adapter-path adapters, and that's telling it to go load the adapters from the other file. So if we run that for a second, it's going to bring us into our chat mode, and now I can ask it questions like I did before. So if I say, what's 8895 plus 631 divided by -659 plus -952. So if we ask that question, and you see now it's gone and done it, right? I mean, this is incredible, right? This is a 1.5 billion parameter model who didn't know how to do anything 5 minutes ago. But look at what it's done here. Think, problem, what's this? Reasoning. Begin by addressing the division operation, blah, blah, blah. Calculate 631 minus da-da-da. Comes back with the values, substitute. So it's doing all the reasoning within the think. It's came back with the answer, 79420034. Conclude with the result, puts the answer in there, and verify our answer. I mean, that's incredible. This is a 1.5 billion parameter model, and now it's reasoning up at this level. Now, this is Bootstrap. Again, I can ask it other questions like, who is Ada Lovelace? It shouldn't do the thinking in that sense. You see, Ada Lovelace was a pioneer, blah, 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 blah. It's not a great answer. It's not a long answer. Remember, in my mixed data set, I was given short answers, so it's coming back with short answers. So if I was to build this up with verifiers and cold starting data sets, for those who is type questions, for summarized type questions, I would need to have equivalent chains of thoughts in the same ways I've done with those math questions. So I really start from the math ones, and I do the same for code, and then I just build up, and that's why you end up with like 1,000 rows of data. Because if I can get to a few thousand rows of data of Coldstart data, then these are going to start to give really good answers, and then I can have reason. You see in the who is question, it didn't attempt to reason at all, but when I ask it a math question where it knows it has to reason, it is now doing the reasoning. So I think community-wise, one of the things that we should really be trying to look at as a community is try and get to an open source set of Coldstart data that anybody can use to pick up those models. And again, you can use the techniques that I did. Again, I'm going to do some other videos to cover other things at some point. And you can see the power of this. That was a 1.5 billion parameter model, and it's doing PEMDAS. And again, if you go to the older models, like the Mistral models of 6 months ago, etc., they were getting these answers wrong. So now you're going to be able to sort of train those models with better answers. And again, I think this is just going to enable a whole sort of fine-tuning type community. Again, I can ask it any other question, so I can say calculate the result of the expression. Let's go with 9109 minus 3701 divided by minus 5634 divided by minus 2070. And then it's came back with 91090177. Now, if I just ask ChatGPT the same question, so I've asked the O1 model, calculate the result of this. Look at this. It's taken a long time to come back with that answer. It's taken 1 minute, 1 second. Divide by this, divide this result by this, blah, 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 blah. And then eventually it came back with 9108, 99968. So basically with 9109. Look at this. This is a 1.5 billion parameter model. It's not fully accurate, but it's a 1.5 billion parameter model. And again, I think if we applied reinforcement learning, it's going to come back with that pretty well. But it's so close. So again, bringing in reinforcement learning, etc., the math capability here is massively improved. And again, if we look at this one here, so what's 8895? Let's ask the same question of ChatGPT. So we'll just go to O1 model. We'll ask it its question here. Let's look at the breakdown. It's done all the kind of PEMDAS stuff, as you say. Remember, the answer here is 794200. 0334. Let's see what ChatGPT comes back with. Again, it's taken quite a long time to think, break down the calculation. This is a 1.5 billion parameter model. It did it fairly quick, if you remember. I just typed it in. It came back fairly quickly. Again, it's got a little bit of rounding going on here. Let's see what it came back with. 794204. 7942.0.334. That is pretty darn good. So hopefully you get the power of this. This is an incredible technique. And I haven't even done any reinforcement learning on this yet. This is just using Coldstart data there. So again, I think it's pretty cool. In a future video, we will do reinforcement learning and see if we can get this even better using kind of rejection sampling. But hopefully you can get from this that actually the technique that DeepSeek R1 is using for the Coldstart data is pretty powerful, and we can start to do that itself. Again, all of the code that I put there is open source. It's on my GitHub. You can go ahead and use this, and you can go and reproduce the experiments for yourselves. So again, if I come back to the original paper for a second, the two things that really was important here was this Coldstart. So section 2.3, reinforcement learning with Coldstart. Two natural questions. Can reasoning performance be further improved by incorporating a small amount of high quality data as Coldstart? That's exactly what we just did. And how can we train a user-friendly model that not only produce clear and coherent chains of thought, but also demonstrates strong general capabilities? So those chains of thought were pretty strong and coherent. You've seen it was like step 1, step 2. It wasn't rambling all over the place there. And then we've done exactly what they did. Unlike DeepSeek R1, prevent unstable cold start phase of RL training. You saw from this version, we were completely unstable as a base model. With that sort of 1,000 type example, well, 380 examples with 3 epochs with long chain of thoughts, you can see it was coming back with the right answers. It was also doing the verification in there. So you see here directly prompted models to generate detailed answers with reflection and verification. We prompted it for reflection and verification as well. Readable formats. And then in this work, we collect thousands of Coldstart data. So if I increase that data set, we had different types of problems. We went beyond math, we did code, etc. We would get the same answer. So again, I think I've reproduced what's happening with the Coldstart pieces. What we haven't done is then ran that through the reinforcement learning. But again, I think we can do that maybe in a future video. So once they've done that Coldstart, they then do the reinforcement learning. And I think I'll show you how to do that in a future video. But I think it's pretty cool that we can do this already. Anyway, I hope this video has been useful, and I'll catch you on the next one.